And worst of all, this string theory that seemed to be everybody's great hope in the mid-'80s turned out to have five theories. This type 1, type 2A and B, and the heterotics. Those combine the 26 and the 10-dimensional one, the bosons and the fermions together. So, and then the 7D supergravity, which got everybody all excited for a while, was going nowhere and so on. So then in 1995, there was this breakthrough.
To solve the problem, Witten constructed a spectacular new way of looking at string theory.
Ed announced that he had thought about it, and moreover, he had solved it. He was going to tell us the solution to every string theory in every dimension, which was an enormous claim. But coming from Ed, it was not so surprising.
The atmosphere was electric because all of a sudden, string theory, which had been going through kind of doldrums, was given an incredible boost, a shot in the arm.
Ed Witten gave his famous lecture, and he said a couple of words that got me interested. And for the rest of the lecture, I got hooked up on the first few words that he said and completely missed the point of his lecture.
I remember I had to give the talk after him, and I was kind of embarrassed too.
Ed Witten just blew everybody away.
Ed Witten blew everybody away because he provided a completely new perspective on string theory. From this point of view, we could see that there weren't really 5 different theories. Like reflections in a wall of mirrors, what we thought were 5 theories turned out to be just 5 different ways of looking at the same thing. String theory was unified at last. Witten's work sparked a breakthrough so revolutionary that it was given its own name, M theory, although no one really knows what the M stands for.
What is the M for?
M theory.
M theory.
M theory.
M theory.
The M theory.
M theory is a theory.
I don't actually know what the M stands for.
Well, the M has
I've heard many descriptions.
mystery theory, magic theory,
It's the mother theory.
matrix theory.
Monstrous theory. I don't know what Ed meant.
M stands for magic, mystery, or matrix, according to taste.
I suspect that the M is an upside-down W for Witten.
Some cynics have occasionally suggested that M may also stand for murky, because our level of understanding of the theory is in fact so primitive. Maybe I shouldn't have told you that one.
Whatever the name, it was a bombshell. Suddenly, everything was different.
There was a lot of panic, if you like, realizing that big things were happening and all of us not wanting to get left behind in this new revolution of string theory.
After Witten's talk, there was renewed hope that this one theory could be the theory to explain everything in the universe. But there was also a price to pay. Before M theory, strings seemed to operate in a world with 10 dimensions. These included 1 dimension of time, the 3 familiar space dimensions, as well as 6 extra dimensions, curled up so tiny that they're completely invisible.
Well, we think these extra dimensions exist because they come out of the equations of string theory. Strings need to move in more than 3 dimensions. And that was a shock to everybody, but then we learned to live with it.
But M theory would go even further, demanding yet another spatial dimension, bringing the grand total to 11 dimensions.
We know that there would have to be 11 dimensions for this theory to make sense. So there must be 11 dimensions. We only see 3 plus 1 of them. How is that possible?
For most of us, it's virtually impossible to picture the extra higher dimensions. I can't. And it's not surprising. Our brains evolved sensing just the 3 spatial dimensions of everyday experience. So, how can we get a feel for them? One way is to go to the movies. familiar with the real world having 3 spatial dimensions. That is, anywhere I go, I can move left, right, back, forth, or up, down. But in the movies, things are a bit different. Even though the characters on a movie screen look 3-dimensional, they actually are stuck in just 2 dimensions. There is no back, forth on a movie screen. That's just an optical illusion. To really move in the back, forth dimension, I'd have to step out of the screen. And sometimes moving into a higher dimension can be a useful thing to do. So, dimensions all have to do with the independent directions in which you can move. They're sometimes called degrees of freedom. The more dimensions or degrees of freedom you have, the more you can do. That's right. And if there really are 11 dimensions, then strings can do a lot more too.
People found fairly soon that there were objects that lived in these theories, which weren't just strings, but were larger than that. They actually looked like membranes or surfaces.
The extra dimension Witten added allows a string to stretch into something like a membrane, or a brain for short. A brain could be 3-dimensional, or even more. And with enough energy, a brain could grow to an enormous size, perhaps even as large as a universe. This was a revolution in string theory.
String theory has gotten much more baroque. I mean, now there are not only strings, there are membranes. People go on calling it string theory, but the string theorists are not sure it really is a theory of strings anymore.
The existence of giant membranes and extra dimensions would open up a startling new possibility. That our whole universe is living on a membrane inside a much larger, higher dimensional space. It's almost as if we were living inside a loaf of bread. Our universe might be like a slice of bread, just one slice, in a much larger loaf that physicists sometimes call the bulk. And if these ideas are right, the bulk may have other slices, other universes that are right next to ours, in effect, parallel universes. Not only would our universe be nothing special, but we could have a lot of neighbors. Some of them could resemble our universe. They might have matter and planets and, who knows, maybe even beings of a sort. Others could certainly be a lot stranger. They might be ruled by completely different laws of physics. Now, all of these other universes would exist within the extra dimensions of M theory, dimensions that are all around us. Some even say they might be right next to us, less than a millimeter away. But if that's true, why can't I see them or touch them?
If you have a brain living in a higher dimensional space and your particles, your atoms, cannot get off the brain, it's like trying to reach out, but you can't touch anything. It might as well be on the other end of the universe.
And it's a very powerful idea, because if it's right, it means that our whole picture of the universe is clouded by the fact that we're trapped on just a tiny slice of the higher dimensional universe.
The idea is that with Witten's ideas, strings were suddenly turned into p-branes. And p-branes could be zero-dimensional points, they could be one-dimensional strings, they could be two-dimensional membranes, like, that's where the name brains comes from, membrane, short for membrane. Or way up to much higher dimensions. So it generalized this whole idea. And so string theory then is became not a theory of strings, but actually these multiple dimensional entities called pre-branes, ranging from all these multiple dimensions from 0 on up. And again, this young physicist, Arkady Hamann, says particles and strings are just different aspects now, from this point of view, are just different aspects of the same thing. And this is the most important theoretical development in 20 years, he says. So this is the idea. This would be a 3D p-brane. All right. But in the meantime, they're working on this. They're all excited. And then in 1998, about a few years later, some enterprising astronomers and cosmologists and astrophysicists decided that they were going to go out and measure the universal expansion. Because they figured with the way things looked at that time, with Einstein's theories, the Big Bang should be slowing down, and eventually we're going to come to the big crunch. And we talked about this the last time. This causes a lot of problem, though, with the physicists, because all along they knew their calculations for the energy that would cause this expansion was way, way off. 120 magnitude of 10 times 120. That's just ridiculous. 120 orders of magnitude is what I was trying to find. And supersymmetry cut that down to 60, but when these guys measured it, it turned out way, way low, and it just seemed like it's impossible to deal with that. The equations won't work. So the idea, though, was they could find a way around it. So they had to live with this cosmological constant. Well, this is what then that Big Bang diagram looks like with the acceleration. You can see it sort of starts to curve because the acceleration started about right here, they figure. And it turns out that the energy involved was really good news for the cosmologists, because remember that inflation thing is what they call a rolling scalar field. And as the universe grows cooler and cooler, the scalar field comes down in value, but they have to use this thing they call omega, which is a measure of the density, because as the universe expands, if it started with a certain amount of matter, what happens to the density? It gets lower and lower, right? And so they have this to measure this omega, and they didn't have enough matter. Of course, they found dark matter finally, and that kind of helped a little bit, but it still wasn't near enough. And then when this dark energy was discovered, with this expansion, acceleration, that enabled their calculations to come right down to 120 orders of magnitude. I mean, just so flat and exact, it was unbelievable. So in order for the physicists, the particle physicists, to meet with them, they would have to mass at 120 decimals and in 120 zeros, and then in the 121st decimal have the right number. I mean, it's mind-boggling. It's mind-boggling. So it was really good news for the cosmologists, but it was horrible news for the string theorists, especially for the string theorists, because they had another problem. They couldn't come up with a positive cosmological constant. Now, everything that they did came up with a negative one. Okay. But then this guy Polchinski came along with this idea of D-branes. P-branes could be D-branes if they were connected with strings, with open loop strings, with their ends kind of a mechanism for connecting them there. It's really interesting, but we won't go into it. How can you see this? Open-end strings would have each end connected, can't get off of the brane. Now, open-end ones like gravitons could. They weren't connected to the brane. So this became something really interesting. So they thought they were going to get there, and if they did enough of these, and they had to do a lot of them, here's where they're working with electrons and everything on these branes. But if they did these loops, and they wrapped them around these dimensions enough, they could get a positive cosmological constant, which is what they needed. But it was like a Rube Goldberg machine. It was really, really, really complex. But it enabled them to obtain a positive CC. But in doing so leads to this landscape that we talked about of theories, right? Where you could have all these universes in the multiverse. And that's because of these dimensions, the way this Calabi-Yau has rolled up the extra dimensions. You got to compactify them to hide them because we only see 4 in our everyday observations. They must be hidden, they're thinking. So when they do all this wrapping around with these D-branes and putting these open strings on them and whatnot, and get the cosmological constant, they have like 10 to the 500 solutions. Now, how much is 10 to the 500? Huh?
It's an awful lot.
It might as well be infinite, right? And the idea is that one of those solutions would be our universe. So how it's incredible. They would never be able to find out what was happening. So, and that's because of this inflation. See, when the Big Bang happens and inflation hits, it goes out and it creates all these different universes. Okay, so that leads to the anthropic principle, which says, well, we're on one of these universes. We don't know which one. We're on a slice of the bread in the bowl, kind of thing. But the only reason that we're here in this universe is because if the universe didn't have the values that it has, we wouldn't be able to be here to observe it. So just like germs grow in a petri dish when the conditions are right, we happen to be and we're looking at our petri dish and thinking that's the universe, but it's really not. There's all these others possibly. So there's a lot of people who hate that because that just says there's nothing unique, nothing special about. We're just bugs in a petri dish. There could be all kinds of things. So this is really kind of an idea of what happened before string theory. See, here's, we'll call them Team Macro, the guys, the cosmologists, using Einstein's equations, Friedman equation, and Goose inflation. Alan Goose came up with this idea of inflation. The Brits hate it, but it works. And so with the scalar field rolling down and everything, they come, and they happen to be just right on, exactly. Whereas Team Micro, with their calculations, are 120 orders of magnitude off. Well, these guys can't get started because their equations break down at the Big Bang. But if somehow they could get started, they could hit it right on the nose. These guys get started really well because they use renormalization and string theory to solve those infinity problems. But when they calculate everything, they're 120 orders of magnitude off. Now, if there's supersymmetry, that knocks it down to 60 orders, but it's broken, so they don't have much hold of that. And so, but this is where that observed omega is. So Team Macro gets precise expansion history of the universe, but can't get started. And Team Micro gets the good start, but expansion history is way off. And then they add the Calabi-Yau and the D-branes, and hooking those things to the D-branes, and they get the landscape. So that didn't help them at all because you got 10 to the 500 possibilities within those 120 orders of magnitude. One of them might be right, but which one isn't? So that didn't help them. So they're kind of in a pickle there. But there was this alternative possibility now. Instead of viewing mass along that Planck scale that we were looking at, this mass hierarchy, where the big stretch that they couldn't explain is, they're thinking, well, we could look at gravity as instead of being at this huge energy, it's just weak. It's leaking somewhere. View gravitational forces weakened by something else, by leakage through large extra dimensions configured as brains. Now, we didn't get to look at all of what Brian Greene was explaining there, but he was going to explain how Witten's thing made it possible to take strings and make like inner tubes out of them and put enough energy that the center of the inner tube disappears and it's a brain, right? And so anyway, this is kind of what it looks like from the open string perspective. They could be on various brains. They could be on the same brain. This would be positive and negative. When a string breaks together and hooked on here, it comes together. It forms an open string that propagates off of it, and so on. So with these ideas, they can come up with this gauge theories and the standard, pretty close to the standard model, and then And then with the close strings, they can come up with the gravitons to include gravity in their theories. So, and then they come up and say, okay, we can have these large extra dimensions, we can have them warped and whatnot. And so they started another revolution based on these brains from 1995. See, so before Ed Whitten, we had 5 string theories and 11D supergravity. After Whitten, then the 11D M theory with its multiple dimension P brains. After Polchinski, the landscape of possibilities with D brains, and now this Arkani Hamad and a couple of other guys, Greek guys or something, I don't know, I can't pronounce their names, but that's what Arkani is the A here and D is the other 2 guys. They have these large extra dimensions, and then Lisa Randall and Sundrum came up with something called warp D brains, which is even more. Some people consider it off the wall, but other people are pretty excited about it. So we got this add D brain, I called it. The extra dimensions are not visible because they're small. Some of you might have read these books. Lisa has a book out called Warped Passages. These are some of the books we're going to give away, by the way. You guys can bring your teachers and your friends. We'll be giving away prizes here. So when you come, you get a book. You know, this is a really good book. There's several out there. Of course, Hawking wrote the one, Brain New World, and so on. But they're not invisible because they're all wrapped up in that Calavial. They're invisible because they're stuck. The extra dimensions we can't, you know, like Brian was saying, Brian Green, you might as well be on the other side of the universe because you can't reach through to another dimension. And the particles that make up matter are stuck to this brain, whereas gravity can leave them. So we only see R squared, whereas maybe the true thing is R to the third, 1 over R to the third, or it may decrease to 1 over R to the fourth or something else, instead of just 1 over R squared. Yeah.
This might sound silly, but we can only go like to the future. Is there like infinite, like, what do you call it, dimensions of time that we don't see?
Yeah, that's very interesting.
I know that sounds, but
yeah, they're trying to find out whether, but it seems like the arrow of time just goes in one direction so far. But at any rate, this has this bulk to deal with it, so it's really, you know, really not small. It's 1 millimeter, relatively small to us, but compared to the 10 to the minus 33 centimeters is really very large. So the idea is that the gravitons leak off into this bulk, okay, and whereas the others are confined. Now in the RS brain universe, she has this idea of a warp.
Okay, well, when people hear about 10-dimensional hyperspace, they say, wow, maybe I can jump into my starship and go into these higher dimensions. But then they're rather disappointed when they find out that these dimensions are very tiny, very small, too small for an atom to get into. However, there is something now called M theory, which is generating a lot of excitement. So tell us a little bit about the differences and the similarities between string theory in 10-dimensional hyperspace and something called M theory.
Well, I'm not. M theory really has string theory in it, but I think what's actually very important that sort of M theory brought home to us more is that string theory itself isn't just the theory of strings, but actually is a theory that has not just strings but membranes. And strings are objects that are extended in one dimension, whereas you could have these objects that we call branes, which are like membranes, that are in string theory, and they can be extended in more dimensions. So you can have branes of various dimensionality. Now, what do I mean by that? Well, for example, you can imagine, say, a curtain in your house, which is a two-dimensional object in a three-dimensional room. And one reason these branes are important, at least from my perspective, is that there's actually mechanisms in string theory to confine particles to the brane. Now, what that means in practice is that although we know that there are extra dimensions, say, in string theory, it might be that not everything actually explores those extra dimensions. It might be that things like electrons are stuck on a brane. They don't necessarily see all the dimensions, they don't travel there. And if they interact with the photon that's stuck on the brain, the photon doesn't spread out. The electromagnetic force won't spread out into the other dimensions. So brains really not only change the fundamental nature of string theory, because it's not just strings, but they also change our idea of what things would look like if these extra dimensions exist. Because rather than say that everything has to be going through all of the dimensions, it could be that various particles only experience a fraction of the dimensions, and there could even be other brains that hold other forces and particles that we don't detect at all if we're stuck on our brain.
Okay, now M theory is defined in 11-dimensional hyperspace, one extra dimension, yet we live in a 3-spatial dimensional universe plus time. So could you explain to us how the rolling up process is done, and
the what process?
How the rolling up, the compactification process works, and how some of these dimensions could be rather large. They don't have to be small at all.
Well, okay, so let's go back to just rolling up the dimensions. And, M theory just has one more dimension than string theory, which already had way too many dimensions. So basically with M theory, you have to roll up one more dimension. But so the picture we had before was that one reason you don't see the other dimensions is because they're curled up to such a small size you can't actually detect them. And we just mentioned, however, that there's another reason you might not see extra dimensions, which is that particles could be stuck on a brain. Now, I should be careful when I say particles can be stuck on a brain, because it's important to keep in mind that basically we know mechanisms to trap most particles on brains, but we don't actually have a mechanism to trap gravity onto a brain. So gravity is always connected with the entire space. In fact, Einstein has told us that gravity is connected with the geometry of space. So it wouldn't make sense to say that gravity is stuck on a brain. But it does make sense to say electromagnetism, for example, is on a brain. Now, what that would mean is that whereas before we might have said, well, so let's suppose we ask ourselves, how big can the extra dimensions be? Well, without brains, we would have said for a limit might be set by the fact that if electromagnetism was spread throughout an extra dimension and an electron lived in an extra dimension, we would actually see consequences. And if we ask ourselves, we've tested up to energies about 100 times the proton mass. So if we say that we know everything that's going on in energy up to that energy, we can actually set a limit on what the size of the extra dimension would be. And although it might sound very stringent, in some ways it's not as bad as you might have thought. It's about 10 to the minus 17 centimeters. The reason I say it's not as bad as you might have thought was based on just gravity itself. You might have thought it was 16 orders of magnitude smaller. But that bound that I just gave you, and that's a very small, 10 to the minus 17 centimeters, isn't the same bound that you would get if you have brains. Now, the reason for that is if you have brains, then electromagnetism can be stuck on the brains, and that means they don't travel in the extra dimension. So before, actually, one way that we could have ruled out having dimensions that were bigger than 10 to the minus 17 centimeters is we would have said that there would be partners of the electron that carry momentum in those extra dimensions, and we would have seen them. And we haven't seen them. But if the electron is stuck on the brain, then it's impossible for a partner of the electron to have momentum in the extra dimension. It's stuck on the brain. It just never goes into the extra dimension. Now, what that means is that the size of the extra dimension is only constrained by the things that actually travel in the extra dimension. And if you want to have the weakest bound possible, you can have everything bound on the brain except for gravity. And then the bounds on the size of the extra dimension have to do with how well we study gravity. And the fact is we haven't studied gravity all that well. We actually only know about gravity down to distances of about 1/10 of a millimeter now, which means that if we have a brain, we can actually get away with much larger dimensions than we thought. And actually, so it's even more dramatic than that if we have brains, and this is some of the work that Raman Sundram and I found. Because if you have a brain, from Einstein we know that if you have energy anywhere, it will affect what gravity looks like. And what we found is that you can have a scenario with a huge brain sitting in with one extra dimension, for example, in which gravity stays highly concentrated near the brain. So whereas before we used to think gravity just has to spread out everywhere equally, if you have brains, you then start distinguishing some directions from others. So not only is there this effect that you can actually have things stuck on the brain, but you have another effect of brains, which is that they affect the gravitational field itself. And we found that that could itself allowed an infinite extra dimension. You can actually have a fifth dimension of that is infinite in extent. And you would have thought that was ruled out because gravity would spread too much into that extra dimension. But we actually found that isn't necessarily the case when you have warped or curved geometry. So brains really do introduce some very dramatic new possibilities.
All right, but now, so this is the whole thing. This is what we want to get from this. Is this whole idea of dimensions, right? That everybody's wrapped around the axle with. See. So I took this from the music band. Total starts with capital T, and that rhymes with D, and that stands for dimensions. Extra dimensions, that is. Not pool, but extra dimensions. And so string theory needs 11 space-time dimensions. Supersymmetry needs another quantum dimension for every string dimension. And then M theory takes another quantum dimension because of the supergravity and whatnot. And then we have, I wish I could read. The whole idea is we have to compactify these things. And if we do, then we get this 10 to the 500 solutions. So Lisa and Arcani, they have this other approach that people are pretty excited about. We wouldn't have to compactify them, but they don't say anything about these. What would happen with these? I haven't been able to find out what the deal is. You know, I think what they're saying is that they just model. They're just modeling the universe because they would have the same problem with the vacuum. See, trying to find the vacuum.